the MOSFET bias circuit shown. It's going to look like this. Now, for this circuit, we're asked what value of RD in kiloohms is needed to allow the maximum possible peak-to-peak signal swing on the drain without clipping. So let's highlight some key things. We're asked what value of RD. So we're going to be looking for a resistance. It's in kiloohms, and it's needed to allow the maximum, this is the next important part, possible peak-to-peak signal, and we have swing on the drain without clipping. So to solve for this part right here, and we'll do this as step 1, and it's going to be incomplete. We need to achieve the maximum swing signal, we need to bias the VD in the middle of its range. So basically, we are going to take the max value, so VD max, and minus from VD min, and then we're going to get some value, and that is going to be our voltage. And then we are going to put it over our, well, we're not going to put it over our ID specifically. We know to solve for this, this would be the voltage of our D. This would be the VD, our new VD, that would allow us to get the maximum possible peak to peak. And so to solve for our RD, which is what we want, we are going to say that our RD is equal to the source voltage, which is our VDD, minus the VD over the resistance where it's over, which is, or sorry, since we're using Ohm's law, instead of this resistance, it's not going to be resistance, it's going to be the current it's over, and the current here is our ID. So that is how we would solve for this. Now, we know a couple of things. First off, we know our source voltage. That is VDD. So we can replace this right here as 14. And our VD max, well, the max voltage going in here can be 14 volts, right? So our VD max is just going to be 14. We have minus, but we don't know our VD min yet. We need to actually go and find this. So this is what we are going to be looking for. And well, the VD min, we can solve for it in a second. We are not given the ID either from the looks of this problem. So we can just solve this as well. So we have two unknowns and we need to solve them. The first, we will look at our VD. So solve for VD. Well, our VD is right here, and we have a VS right here, and we also have a VG right here. So we could look at this node, however it's a little bit different and we're not going to actually do that. Instead, that was the first thing I thought of, but the next thing I thought of is actually looking at the circuit. Looking really closely at this circuit, we have our VD here, that's the voltage that we want to find. We know we have some source voltage here, and then we have this resistor value, and we also have this resistor value. And we can see this is going to form a sort of voltage division. It's going to pull some of this VD away. So if we do this, right, because the circuit's a little bit sideways right now, but if you were to rotate it, it might be a little easier to see the voltage division. Anyways, what we would do here is we would say, well, our VD is equal to the source voltage, which is our VDD, and then we're going to multiply this by our RG2, and the reason why it's RG2 and not RG1 is because if we were to, let's say, rotate this, right, we have our VDD right here, we have our VD right here. We're not going to worry about the RD because the VD is the voltage over the resistor right here. So we have our VD like this, and then we are going to have our RG1, and our RG1 is going to act like right here, and then we're also going to have our RG2. And the way we would draw this is that this VD would be over this part right here, and this part would be right here. So looking at that, we're going to have our RG2 right here. And our VG is not going to be inside of this little circuit diagram that we have right here. So we just have our RG2 up top, and then we have RG2 plus RG1. like this. And so this is going to be our voltage divider. And this means that our VD is equal to, if we do the math on this, a solid 6.554 volts. So we can take this and replace it with the VD there. So we have 6.554, and this is all volts up here. Now, what else do we need to find? Well, we need to look for our ID. And to find our ID, we are going to use some equation that we have in the notes linked below the like button. And to solve for our ID, we need to look at our circuit. So our ID, we can see it's going down here, right? And it's going down still this way, so it's kind of in series with our I of S. Well, that means that our ID is about equal to our I of S. And our I of S is equal to the Vs over the Rs. And this is important because we're actually given our Rs right here. However, we don't know our V of S, so we need to find this. We're going to have 6.5 kiloohms, and now let's look for our Vs. And so when we solve for our Vs, we can look at what we were talking about earlier, this node right here. We didn't do it for our VD, but we're going to do it for this one right here. So we have this node here, and we know that the output is going to be our Vs. So we're just going to put our Vs like this, instead of equal to, well, our ID, or the VD, is going to be going into this node, right? We know our Vs is going out. So if we were to switch it to the other side, it would be like a minus. Our VGS is also going out, right? So we have our voltage source, the Vs, or the VD. So VD is going in, so that's a plus. And then we are going to have minus our VG. And well, what is our VG? Well, VG is really VGS. This is the gate source, right? And our gate source is looking this way. And well, since our gate source is looking this way, what we're going to do is we're going to say, well, remember what we were given up here. So V on is equal to our VOV. And VOV is equal to VGS minus VT. And so if we substitute this in and we rewrite this a little bit, our VOV, which is the overdrive voltage, is something that we're going to have to find. Our VOV is given to us as 0.26, and then our VGS, that's again what we want to find, so we're going to put the VT on the other side, so we have a plus. Our VT here is 0.7, and this is equal to our VGS. And this is going to give us a 0.96 volts for our VGS. So now that we have this, we can plug it back in here. And so our Vs is going to equal to, well, if we plug this in, if we know our VD as well, our VD is we found to be 6.554 from here. So we're going to have Vs minus 6.554 minus 0.96. And if we were to plug this into our calculator, we would get that our, and we'll just keep going up this way, and we will draw this up this way, we would get that our Vs is equal to 5.594 volts. So that is the source for our Vs. And now we can put it in here. We're going to have 5.594 volts. And then we could just divide these out. And that's going to give us an ID or an IS. We're looking for ID here because, well, we want to plug it in for right here. It's going to give us an ID equal to approximately 0.8606, and we're writing this in milliamps. So this is going to be our ID. It's the next value that we have just found. So the steps for this would be setting this up right here. That would be step 1. And then we need to find our Vs. So step 2 would be going over here and solving for that Vs. Realizing that we need our VGS, we would go down here. This would be step 3. And then we would plug our values in to this equation right here. That'd be step 4, where we bring this in here, like we were talking about earlier, and then we would go and arrive at this, step 5. And then after step 5, we would encounter a step 6, which takes us back here, plug it in back to our original equation. So that's how we would look at that. Now, we have our ID, so we could plug it in to our unknown right here. It is now going to be a 0.8606, and it's like 10 to the negative cubed, because that's what milliamp is. We could always just throw that up top to be 10 cubed. Now we need to find our VD min so that we can find our VD. So step 3 is going to be looking for our VD minimum. And to solve for our VD min, if we look at the notes linked below the like button on page 80, we have it for an NMOS in saturation. We have our VDS has to be greater than VGS minus VTN. So the standard one is VDS has to be greater than or equal to VGS minus our VTN. Well, for our scenario, we want our VD min to be greater than or equal to. Our VGS is going to be the VD, because that's the source. That's what the GS stands for, the source. Our source here is VD, minus our VTN. So we're going to have just VT. And so we are going to have that our VD minimum has to be greater than or equal to the VD, which we found earlier, to be 6.554. That's not the actual VD minimum. That's not the actual VD that we're going to be using right here. To solve for that, we would need all of this right here. It's a little bit complex, but you can always go back and watch it if you need a refresher. So we have 14 minus the VD min. The VD min is what we're looking for now. And so the VD min has to be greater than our 6.554. That's just the VD that we have right here. Now the VD that we're plugging inside of the equation right here is the one after we have all of these values set up. So that means we're going to have to subtract our VT, which is 0.7. And after we do this, we are going to get an approximate value of about 5.854 volts. And so that means our VD minimum is going to be 5.854 volts. And so we can say that this is what that is right here. So hopefully that all makes sense. If it doesn't, you can always watch it back, and all the steps are labeled out very clearly. Now we'll take this subtraction right here, because the subtraction is, if we want to bias VD in the middle of its range, we would do this. We are going to get the 9.927 volts here, and then we are going to plug that straight into here. So we have 14 minus 9.927 volts, and this is over 0.28606 times 10 to the negative 3, which is the milliamps part. And if we do this, and if we just turn the milli into a kiloohms, we are going to get the following as our value. So our RD should equate to about 4.7 kiloohms, and that's the max, or that's the RD for max voltage output swing. And the reason why, again, we do this very first part is because the maximum possible peak-to-peak signal swing on the drain without clipping needs to be found. So that's how we would look at this problem.